In this chapter we will be studying radical and absolute value functions. In this lesson we are going to look at the absolute value of quadratic functions.
Alright, well, now this being the course that it is, we are going to find the absolute value of a quadratic. Okay, so, and you probably should have expected that. So the way you do this is very similar to the way we were kind of finishing off the previous lesson. When you take the absolute value of the quadratic, essentially what happens is any part of the quadratic that dips into quadrants 3 and 4 gets reflected back up into quadrants 1 and 2. So essentially what we're going to do first of all, and this sets it up really quite nicely here, determine the characteristics of the quadratic function without the absolute value. In other words, if you got the absolute value of a quadratic, first thing we're going to do is we're going to take a look at it. Just ignore the absolute values for the time being. What does it look like without? Then what we're going to do is we're going to identify the x-intercepts. Now those are invariant. Those are always going to be invariant. Okay, those same points are going to be on the graph with the absolute value and without. Then we're going to take a look at the y-intercept. Now if it's positive, it's invariant. It's going to stay the same. But if it's negative, it's going to switch to a positive. Anything that's below the x-axis, anything that's in quadrants 3 and 4, is going to flip up. Okay? Now that means that the y-coordinate is the one that's going to change signs, not the x-coordinate. The x-coordinate determines the value of what's inside the absolute value. And when you take the absolute value of it, that is how you're determining the y-coordinate. The y-coordinate shouldn't be negative because it's going to be equal to, it's always going to be y is equal to the absolute value of some function. So if y is the absolute value, the y-coordinate should be positive. Same thing with the vertex. We're going to determine the vertex, and again, if it's under the x-axis, then we're going to flip it above the x-axis. We're going to make the y-coordinate positive. But if it's already positive, we're not going to worry about it. But in that case, either way, that is going to become this local maximum value. So we're going to plot the above characteristics, and then we're going to graph it. Okay. If you're going to graph the absolute value of the function, any portion of the graph below the x-axis becomes reflected over or on the x-axis. Okay? Now it's not a particularly hard thing to do. It's going to look a little weird to begin with, but eventually you're going to see that we just keep doing the same things over and over and over again. So let's take a look at some examples. Okay, so right now we're taking a look at y equals x squared minus 6x plus 8. Okay. In a second here, we're going to take the absolute value of it. So this little example that we're taking a look at here is going to kind of walk us through bit by bit. It's more of an illustration actually than anything else here. So x squared minus 6x plus 8, if you were to complete the square on that, you'd get y equals x minus 3 squared minus 1. So our vertex here is going to be the point 3, negative 1. Our y-intercept here is going to be 8. And the x-intercepts here, if you write this in factored form, okay, would be x minus 2, x minus 4. So we're going to get x-intercepts here at 2 and 4. So when you plot that, you get a graph that looks a lot like this. Now notice that part of this graph dips below the x-axis. I can see it in quadrant 4 here. The absolute value is going to change that. Okay. Now the y-intercept is positive, so the absolute value is not going to change that. The x-intercepts, the absolute value is never going to change those anyway. Those are invariant. But it is going to change this point right here because I no longer want it to be in quadrant 4. So I'm going to flip it over and it's going to go up to there. I'm going to get this little bump. This part's going to disappear. And so that point there that was 3, negative 1 is actually going to become the point 3, positive 1. And actually when you take a quick look at what that looks like over here that's done for us, you can see that's exactly what happens. We get this little bump right here. Okay, and when you put the absolute value around it, that's all it does is it takes that original function, reflects over those parts that drop below. Now I've got this local maximum point here. Now what I mean by that is the vertex here, to the left of it, it rises up to that point, to the right of it, it drops down. So this is a little peak. Right there, it's what we call a local maximum. You're going to come back to that kind of terminology over and over again later on in this course and the next couple courses you take. Notice that the y-intercept was positive, so it stayed the same. The x-intercepts were both invariant as well. Okay, That's what that absolute value function looks like. Now I want to take us one step further with this, and we're actually going to see what happens with the piecewise function. Now, in the previous lesson here, you'll remember that what I did is I broke up the intervals along the x-axis here. Well, we've got a couple of intervals here. This right here, from this x-intercept on, this is where x is greater than or equal to 4. This one over here is where x is less than or equal to 2. Now, the reason I highlight these two on their own here is because for these guys right here, the absolute value function and the original function were identical. The absolute value function had those two arms, so did the original function. So for those two arms right there, separate together, they form one part of the absolute value function. Now, this little part in between here, where x is between -2 and 4, this is where the absolute value changed the function. This is the part that no longer matches up with the original. So something has happened there. Now, I want you to think about the way absolute value, piecewise functions, I should say, work. Or in this case, it's going to be the absolute value, but the way the piecewise function works here. With the piecewise function, the way what we did here is we started with the original. So the absolute value, think about it like this, the absolute value of x squared minus 6x plus 8, which is y in this case, is going to equal this right here. Now it's going to equal x squared minus 6x plus 8, which is identical. Now think back to the rule that governs the way we treat absolute value functions. It's only identical if this middle part here, inside here, is positive. And by that I mean above the y-axis. Sorry, the x-axis. That occurred where x was less than 2 or x is greater than 4. In other words, what's inside here stayed the same. These two arms right here stayed the same. And where did those occur? When x was greater than 4 or equal to 4, x is less than or equal to 2. Okay? A change was made. We put a negative in front of that function when it was in between those two. This was the part of the function, this was the piece of the domain that changed. And so now, writing that out, it would be x squared minus 6x plus 8. Okay, if x is less than or equal to 2, or x is greater than or equal to 4. Now, don't write the word and there. You may have already seen this in a previous math course. Maybe you didn't, or maybe you just don't remember it. But the words and or actually have very specific meanings in math here. In this case here, we use the word or because you could have points that are either on this side of 2 or this side of 4, but they can't both happen simultaneously. The word and typically means I can find a number here that satisfies both of these together, and that's just not true. So always use the word or there. Or I can multiply that negative through and get negative x squared plus 6x minus 8, and that's going to occur, that's right, in this case they're using the word if we've got 2 less than x less than 4. Okay, so the part that's above the x-axis, in this particular case here, didn't change. That's how I identify it. This is the part that did change. There's our piecewise function. Notice it's slightly more complicated, but really is the exact same thing that we did before here. It's just that now, because of the quadratic, more often than not, we're going to have these two pieces here where we're outside the roots, okay, less than 2, greater than 4, or then in between the roots. All right, in this example, we're just being asked just to sketch the original function and its absolute value on the same grid here. Now, I've said this repeatedly, and I hope it's starting to kind of sink in, that what the absolute value does is it takes any part of the function that shows up in the quadrants 3 and 4 and flips it into quadrant 1 and 2. So here's our x-intercepts here. We got this into 3 different regions here, but these two regions here, when x is less than -1 and when x is greater than 1, the graph was positive, there's going to be no change. Here's the spot right here in between those two where there's going to be a change, because this is the spot that dips below the x-axis. So the lowest it gets down here is the point 0, -1. So when I flip that over, it's going to go up to the point 0,1. So it's going to look like this. And this little piece down here will disappear. So there's the absolute value of that function. Let's take a look at this one. Again, the x-intercepts here are going to help me break this into different intervals here. Now in this case right here, the intervals that I've just identified, these are where the original function drops below the x-axis. This is where this goes into quadrants 3 and 4. So the absolute value is going to flip this up. Now the part that's in between in this case isn't going to change because it's already above the x-axis. It's already in quadrants 1 and 2. So this part right here, think about this. This curve down, it went down. I'm just going to assume this is down at here at -4, so -2, -4. So that's going to flip up to -2, +4. Now I'm assuming the same thing here. This is going to end up being +3, +4. So it's going to jump up to right here. So then from this point, this x-intercept, it's going to swoop up to there. Here it's going to swoop up to there. So this little part right here disappears. When I take the absolute value of that function, it's going to swoop up like this. It's the middle part now that stays the same. Over here, again, our x-intercepts help me break this up into 3 different sections here. So these parts right here, because the original function is up in quadrants 1 or 2 here, now in this case it looks like they're both in quadrant 2, although they're going to extend a lot further as you go up. What's in between, this is the part that's in quadrant 3. That's the part that's going to flip. And from the x-intercept down, we go to the point -3, -4. So that part's going to jump up to be -3, +4. So the graph is going to curve up to there and then down to there. And this part right here will disappear. And now what we're looking at, where it comes down, bumps up, jumps back up again, that's the absolute value of that particular function. All right, these next few questions are a fair bit more involved. There's a lot going on here, so take our time with these things here. So we got to write these things as piecewise functions. We got to identify the range, x-intercepts, y-intercepts, and we're going to sketch this. Okay, and you might as well throw in, we're going to ask for the vertex here too. So let's just jump right in. So to start off with, what I'm going to do is I'm actually going to look at this function right here. I'm going to ignore the absolute values. I already know, even from the previous question here that we just did, I already know what the absolute value does. So let me take a look at what the original function is here. So first of all, I'm going to put this in factored form. I'm going to take out the -2. That's going to give me x squared plus 4x minus 5. Okay, and so now this can be factored. That's going to be x plus 5, x minus 1. So I'm going to get my two x-intercepts here are going to be -5 and +1. Now I already know that my x-intercepts are going to remain invariant. So my x-intercepts here are going to be -5 and 1. So already I can come over here to my graph. I know it's going to be out here at -5 and +1. I can draw those in. Okay, -5 and +1. Good. My y-intercept, I can actually go right to the original function here and I can just come over here. I know it's going to be 10. If you plug if you substitute 0 in for x there, it's going to get you 10 here. So my y-intercept is 10. Up here on my graph, my y-intercept is going to be 10. Okay, this is going up. My y-intercept right here, 10. Now the part that I'm missing is my vertex. So I'm going to now convert this into vertex form. So first of all, I'm going to move that +10 way out of the way, and then I'm going to take -2 out of the first two terms. So it's going to be x squared plus 4x. Now, half of that is going to be 2, right? So if I take half of that 4 right there, I'm going to get to here. Now that means I already know 2 steps down that this is going to be -2 multiplied by x plus 2 squared. I already know that. But now I take that 2, that half of this, and I'm going to square that. So I'm going to add 4, subtract 4 here. I'm going to take that a negative term here because I don't need it to complete the square. I'm going to take it out of the parentheses by multiplying it by the coefficient. So -2 times -4 is going to get me a +8 out here. And so 10 plus 8 here is going to give me 18. So I have got a vertex here at the point -2, +18. Okay, -2, +18. So over here, that's going to be -2, +18. I'm going to slide up here. Here's 60. It's going to be right up here. So this function right here, if I look at a little bit of symmetry, that's going to be, there's going to be a point right there that's symmetric to this point, because there's my axis of symmetry right there. This thing's going to look like this. I just missed it. It's going to drop down like that. Okay, that is what the original function looks like. So what does the absolute value function looks like? Well, it's going to take these parts here that are in quadrants 3 and 4, and it's going to reflect these things up here. Now, I don't have any really points down here to help me with this, so this is basically just kind of a guess at my point, but I have the major points that I need. Okay? That's what this thing's going to look like. Now, notice from 1 on and from -5 on this way, so x, sorry, I hope you can see that here, x less than or equal to -5, x greater than or equal to 1, that's the portion of the function that had to change. But in between here, okay, between -5 and 1, that's the part that didn't change. Now, normally what I do is I actually am going to take it like this. I'm going to take those away here. Normally what I will do is I will put the or equal to just onto the part that didn't change. That's just a choice that I make, but that's normally what I would do. Now, because I'm trying to build the piecewise function right now. I've already got the graph. I've already got the graph of the absolute value that I need. What I'm going to do right now is turn this into a piecewise function. Now, let's bear in mind what happens here normally. When I write this out, normally the way I write the piecewise function is the very first line is identical to what shows up in between the two absolute value symbols. This is the part that didn't change. Along my graph here, which interval didn't change? Well, that was the part between -5 and 1. So up here, I'm going to say that's between -5 and 1. And this is where I would typically put the or equal to. My second line here is the part that does change, and I'm going to put a negative in there. And that's going to occur when x is less than -5 or x is greater than 1. Now, unfortunately, I would like to write that out in a straight line there, but I don't have enough room for that. So those are the two intervals that together form the parts that change. Now I'm going to rewrite this again. This will be -2x squared minus 8x plus 10 when x is in between -5 and 1. Or it's going to be, I'm going to distribute that negative through. Positive 2x squared plus 8x minus 10 if x is less than -5 or x is greater than 1. And there's the piecewise function that I wanted to create. Now I got a couple more questions that I got to answer here. Based on my absolute value, what's the domain? Well, it's going to be an element of the reals. That won't change. But my range will change. And now, and you're going to see this show up an awful lot. Now, it's not always the case, but very frequently this is the case, that the range here is going to be y is greater than or equal to 0. And that is what we're seeing here. The graph drops down to the x-axis. That's where y is 0, bounces up, hits y equals 0 again, and then bounces up again. So those are the pieces that we were looking for. All right, now this question is actually a little bit simpler because of our starting point here. So just like the previous one, I'm going to drop the absolute value so I can see what the original function looks like. And it's already in root form. So I can tell you right now that the x-intercepts here are going to be 3 and -3. And so with that in mind, I'm going to come over here and I'll plot those, -3, +3. Those are the x-intercepts on the graph. The y-intercept, I'll just make x equal to 0. So it's going to be -3 multiplied by 3. That's going to be -9. So on the graph here, the y-intercept here will be -9, way down here. Okay, now I've already got a pretty good sense of what this is going to look like here because of some symmetry, but I'll show you how you figure this out here. I want to figure out what the vertex is, and some of you can probably already guess what it is, but I want to show you anyway here. Notice what's going on here with the x-intercepts. Okay, these are symmetrically, these are symmetrically distributed around the origin here. The axis of symmetry is going to be, okay, x equals, it's typically the average of the x-intercepts here, so 3 plus negative 3 over 2. The answer is 0. So the axis of symmetry is 0. If you want to figure out what the vertex is, you take that axis of symmetry, plug that in for the x-coordinate, and then solve for y. And in this case, you're going to get negative 9. So it turns out that that y-intercept is the vertex. Okay? So the original function is going to look something like this. It's going to curve, wow, I didn't do that very well. It's going to curve up through the x-intercepts there like that. Oh, I've drawn better. That's embarrassing. But anyway, you get the idea. Now, this is going to split this function up, obviously, into these 3 pieces right here. This, from this x-intercept back, so this is going to be where x is going to be less than or equal to negative 3. From this x-intercept forward, x is greater than or equal to positive 3. Now, notice that these 2 parts here are both above the x-axis. They're both positive in quadrants 1 and 2. That part's not going to change. But this part down here, that is in between negative 3 and 3, that part is in quadrants 3 and 4. That part's going to flip back up. So when I throw the absolute value over this piece here is actually going to pop up. It's going to look like this. And now this piece here is all going to disappear. So that's what the graph of my absolute value is going to look like. Okay? Now, let's figure out what the piecewise function is going to look like. Okay. Now, remember how we do this. The piecewise function, normally what I would do is I would simply leave the first part the same. I wouldn't touch it. That's going to represent the part that has stayed the same. Now, when I look at my graph, I know that the part that stayed the same were out here, where x was less than or equal to negative 3, where x is greater than negative 3. Sorry, positive 3. Because that wasn't the part that I flipped. So up here, I'm going to write where this is going to be true, where x is less than or equal to negative 3, or x is greater than or equal to positive 3. The part that changed was the part that was in between. So I'm going to throw a negative there, and that negative is going to apply when x is in between negative 3 and positive 3. Now, because the original function did not have those multiplied together, I'm not going to multiply those together. So I'm not going to worry about distributing the negative through. I'm going to leave it like that. Okay. My domain here is going to be x is an element of the reals. And just like it was previously, y is greater than or equal to 0. That's going to form my range. Okay. Now, notice one other thing here, and it wasn't specifically asked for, but I'm going to discuss it anyway. Notice that the vertex here became the point 0, 9. The y-coordinate changed signs. I flipped that up. So that's what the new vertex is going to be. Okay, one more question in this kind of style. So the first thing again that we're going to do is we're going to drop those absolute values so we get negative x squared plus 4. All right, and this one again, it's kind of similar to the previous one, is already a little bit simple. The reason for that is because I already know what the vertex here is. The vertex is going to be the point 0, positive 4. It's because this is already in vertex form. Okay, so I already know that my vertex is going to be right there. Now, I'm going to put this into root form so I can figure out what the x-intercepts are. So the first thing I'm going to do is factor out that negative, makes it look better, and then that's a difference of squares, so I know this is going to be x minus 2, x plus 2. So my two x-intercepts here will be positive 2 and negative 2. So I'll draw those out over here, negative 2, positive 2, and my graph's going to look something like this. Oh yeah, it's a much better parabola than what I drew previously. Okay, now my y-intercept, I can figure that out here from my vertex form as well here, because when I plug in 0 for x, I'm going to get 4. Okay, That's because my y-intercept here, just like the previous case, my y-intercept and my vertex are basically one and the same thing. Now, I know that my absolute value is going to take parts of the graph that exist in quadrants 3 and 4, I'm going to flip them up. Now, that means from -2 back and from +2 forward, these are the pieces that, whoops, you can't see that. These are the pieces that are going to change. But the piece in between -2 and 2 won't change. And again, notice, this is just me doing this here. But because this is the section that won't change, this is where I'm putting the or equal to. So now this is what helps me build the piecewise function. So the absolute value, these are the parts that are going to change. These are parts that are going to flip up, going to look like this, and that's not perfect, but again, you get the right idea. So over here, to build the piecewise function, my original function is going to look, sorry, what's inside here, remember my first line, I'm going to use the part that doesn't change. That part that doesn't change, we already saw was the part that was in between the two x-intercepts. Then what I'm going to do is I'm going to put a negative in front, and that's going to occur where x is less than -2 or where x is greater than +2. Okay? So there were two parts to that. Okay, two parts that did change. Now, to simplify that, I am going to multiply the negative through because it makes sense in this case. So the part that didn't change, again, was in between -2 and 2. Now I'm going to distribute the negative through to get +x² minus 4. This will be where x is less than -2 or where x is greater than +2. So there's the piecewise function that I was looking for. Okay. Notice that my vertex, in this case, because the y-coordinate was positive, my vertex stayed the same. My domain, and I've seen this a few times, my domain doesn't change, and my range continues to be y is greater than or equal to 0.
Now we're going to practice finding the equation of an absolute value function given its graph.
All right, now we're going to take a few minutes here, and what we're going to do is we're going to take a look at how to grab the function from the graph. Now, think about what we did when we were trying to graph these things. We had the absolute value, so to graph it, what we did is we ignored the absolute value symbols, graphed what's inside, and then we flipped things. Okay, then to get the absolute value, we just, anything that was below the x-axis in quadrants 3 or 4, we flipped up. Well, here we're going to do something very, very similar, just in the opposite direction. I already know, based on this V shape that I'm seeing here, that this is the absolute value of a function. The absolute value, when I apply the absolute value, is taking anything that was below the x-axis and flipping it up. So in this particular case here, one of two things happened here. Either it was this line right now that got flipped, and so this part stayed the same, this part flipped, or it was this. Okay, the line came down like that. It was one of the two. Either that was the original line, or this was the original line. I simply have to make a choice. Now, most of the time, people are going to assume that this was the original line. Okay? And that's only because it's got a positive slope, and for one reason or another, that's just easier to think about. So let's just talk about what happens here, and I'll show you that they are both the same, actually. So if you're going to come up with the equation of this line, first of all, what you would do here is you would figure out what the slope is, and that's what this is all about here. You would figure out the slope, and notice that I've got a x-intercept here of -4, y-intercept of 2, meaning I've gone up 2 over 4. So my slope here was 1/2, and my y-intercept was +2. So this is the original function. This is the equation of this line right here. To go from there to the original graph that I was created, I just put the absolute values around it, and boom, it does this. Okay, so this is the equation of that graph. Now, had you chosen differently, had you assumed that this was the line, as opposed to the one that I just gave here, the slope here would have been -1/2, and the y-intercept here would have been -2. Now, that would have given you this graph right here, and then you'd put the absolute value around it to create the original function that we saw here. So I want to show you that these two are exactly the same. Now what you can do with this graph right here is you can actually factor out a -1, and I'll show you the work over here. And we'll zoom in on that. So here's that second function. You can factor out the negative, and then what you can do, because you've got two factors multiplied together, you can actually take the absolute value of those separately. The absolute value of -1 is just 1, and you're left with the absolute value of 1/2 of x plus 2, which was the original function. Or sorry, which was that previous function, that one up here. So because this is equal to this, and because the absolute value of -1 is 1, it's equal to this, those two functions are exactly the same. So the trick to doing this is to essentially sketch what the original function would have been, come up with its equation, and then just put the absolute values on it. Let's take a look at some examples. Okay, so I'm going to write this equation here with the absolute values in it. So the first thing I'm going to do here is I'm going to assume that this isn't the original function. I'm going to create the original function. I'm going to assume that this line right here reflected down. So this one's going to drop down like this all the way down, and it's going to hit the y-axis down here, quite a ways down here at -6. I know that because the original went through +6. So now the slope of this line, I'm going to go from -6 up to 0. So it's going to be a rise of 6 and a run of 3. So my slope here is 2. So now look what I've got here. I've got a slope of 2, a y-intercept of -6. So the equation of this line right here is going to be 2x minus 6. That's this line. To go back to the original function, I am going to, therefore, put the absolute value around that. Done. Or I could have reflected this part of the line down. Okay? In which case, if I get rid of this, this graph's just going to drop down like that. Now it would have looked better, obviously. I'm just doing that real quick. Notice that the y-intercept here is +6. My slope, to go from here to this point right here, I dropped 6. That's a drop of -6. And I go over 3. So that's a slope of -2. So, or the original function could have been -2x plus 6. And then once again, all I do to get the graph that I'm seeing is put the absolute values around that. Either one of those is totally correct. All right, now in this question we're going to do basically the same thing we did the previous question. It's just that this time we're going to be looking at a quadratic. So again, the first thing that I want to do is I want to take this quadratic and I want to, what's obviously the absolute value of a quadratic, I should say, and get rid of the absolute value from the graph. Now, I figure most people are going to actually make it a parabola that opens up. So we're seeing right now that the vertex here is the point -3, +4. But I'm going to flip that down here, and that's going to become -3, -4. And they'll give me the vertex looking something like this. So we get rid of this. And that's what the original function looked like. Okay? Now, that's not necessarily true. It also could have been a parabola that opened down, but it doesn't really make much difference. Okay, so because there's a fair bit going on in this problem here, I'm just going to stick with this one idea. Okay, so now that I've got it drawn like this, I'm going to write this in vertex form because that's what the question's asking for. So I'm going to write this as y is equal to a x plus 3 squared minus 4. And now to figure out what the value of a is, I'm going to plug in a point there. And I think one of the clearer points on there is this point right here, -1, 4. So 4 is going to equal a times 1 plus 3 squared minus 4. Okay, so to solve for a, I'm going to bring that 4 over. That's going to be 8. It's going to equal a. Then 1 plus 3 is 4 squared is 16. And so a is going to equal, when I divide that, a is going to equal 1/2. Okay, so then I'm going to get the equation y is equal to 1/2 x plus 3 squared minus 4. And now to create the graph of the original function that I saw here, I'm just going to put absolute values around that. Boom, there we go. Now the first question I'm getting asked about this is determine the x-intercepts as an exact value. Now, bearing in mind that the absolute value function and the function without the absolute value will have the exact same x-intercepts, that's what I'm going to do here. So I'm going to look at 1/2 x plus 3 squared minus 4, and I'm going to find the x-intercepts of this guy right here. So I'm going to bring the 4 over to start off with in my the process here of isolating x. Then I'm going to get rid of the coefficient by multiplying. So when I multiply by 2, I'll get 8 is equal to x plus 3. So first of all, I isolate the term that has the x in it by getting rid of the other term. Then I get rid of the coefficient. Now I'm going to take the square root of both sides. Now, because I have to now take the square root of this and get rid of that square there, I don't know if the intention was the positive or negative value there. Then I'm going to subtract the 3. So -3 plus or minus, and I'm going to now simplify root 8, and you've done that one a number of times in this course already. So it's going to be -3 plus or minus 2 root 2. Those right there are the two x-intercepts. So back to my function here. This group, this bit right here didn't change. And so this is going to be where x is greater than or equal to -3 plus 2 root 2. And this over here will be where x is less than or equal to -3 minus 2 root 2. And then the part that's in between, that was the part that changed. So if I'm going to come up with a piecewise function, I'm going to have the absolute value of 1/2 x plus 3 squared, minus 4, is going to equal 1/2 x plus 3 squared minus 4. This occurred, no change, okay, exactly the same graph occurred when x was less than or equal to -3 minus 2 root 2, or x was greater than or equal to -3 plus 2 root 2. It's a little complicated, but bear in mind it's still just x-intercept, x-intercept. Okay, it doesn't matter if it's not this nice, beautiful little -3, +2 sort of thing. Just even though I have to write it a little bit more here, it's the exact same procedure here. I put a negative in front, and that's going to occur when, when x is between these two x-intercepts. Okay, you can't see that. So when x is between -3 minus 2 root 2 and -3 plus 2 root 2. Now I'm going to write this again, this piecewise function again, because I'm going to distribute the negative through down here. And it's important that you catch this, because it's so easy for people to just simply put the negative in front of a part of the function and not the whole function. So it's really important that you catch this one little detail here. It's particularly important because if this was to show up on a multiple choice exam, okay, it would be very easy for us to catch a bunch of people with this one little detail. This second function right here, that negative gets distributed through. It would be -1/2 x plus 3 squared, but the negative also distributes to here. See, a lot of people are going to forget this, and that's going to change that to a +4, and this will occur in between the two roots. And so that's the piecewise function really that we're looking for. Okay, the positive part, be less than the one x-intercept, greater than the other x-intercept. The negative part in between the two roots.